Hey everybody, this is Larry. This is day 11 of the December Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about today's poem. 878, nth magical number. A positive integer is magical if it is divisible by either a or b. Okay, given n, a, and b, find the nth magical number. Okay, and n could be really big, 10 to the 9th, right? So, okay, So A or B? Okay, so my first instinct, to be honest, and okay, so I am solving this live, so if it's a little bit slow, just fast forward. But my first instinct is to do like a breadth first search type thing, like a queue, like okay, you start with A and then you start with 2A, you start with B, you start with 2B, do some kind of heap type thing and kind of sort it out, right? And of course, when you see that n is really big, that's not really feasible. And then my second thought immediately is just binary search. And in this case, there are only two numbers, so I would get into, maybe I'll talk a little bit about the general, maybe not general, but a method to kind of let you figure out how to do it for more than two numbers, right? And that is with something called the inclusion. How do you say? Inclusion exclusion principle, which allows you to kind of calculate the math behind that. But of course, if with only two numbers, I think you can probably come up with how to. Well, okay, let me step back for a second and let me just go over it, right? With binary search, what do we binary search by? Actually, is that, that's really, I mean, I think this one threw me off a little bit, but I think at least in Python it should be okay. Given that, yeah, I mean, we could do some math on the bounds. It may be very big, to be honest, but either way, binary search is okay because, okay. So instead of asking what is the nth magical number, the way that we structure this as a binary search is that given a number, what magical number is it, right? What is this precision magical number it is? And the answer should be relatively I wouldn't say it's straightforward, but you can calculate it relatively easily because you can. So for example, like 2 and 3, so A is equal to 2, B is equal to 3, then your magical number is going to be, I mean, you could sort them, but I'm just going to split them up. So you have 2, 4, 6, 8, 10, dot, right? And then you have 3, 6, 9, 12, 15, dot. And of course, you want to combine them and sort them, and also dedupe, right? And of course, the math is relatively straightforward in this case, where the deduping is A times B is equal to 6. So multiples of 6 are going to happen, it's going to dupe, right? So with that in mind, the formula of given a number, say I have some f of a number, so returns returns k where k is where x where the kth where, sorry, I'm just trying to English this part, where x is the kth magical number, right? And in this case, maybe I'm doing it off by ones. We'll have to kind of think about it a little bit, but you can just do x. This is going to be, this is the number of numbers that are, and okay, let me actually rephrase this for a second. This means that there are k minus 1. Is this 1 based? Doesn't actually tell you per se, though with the example it tells you, but it's a little bit awkward. There are k minus 1 magical numbers smaller than x, right? So wait. So actually this is not true. I lied a little bit. This is what we ideally want, but what we actually have in a function is actually we calculate how many smaller magical numbers, or how many magical numbers are smaller than x, right? And then here, then we can use this formula. Okay, I think this is a little bit more better of a question to ask, because then now you can ask, okay, because the reason why I say this is because why I changed to this is because where from here, you could get from here to this question, but they're not equivalent, right? For example, in this case, between 2 and 3, you can say you have 11, and 11 obviously is not a cave magical number, but we are able to calculate how many magical numbers are smaller than it. And of course, you can do some math about that later. But yeah, so then here to answer this actual question, let's. And the way that I always like to think about it with respect to off by ones is just think about the edge cases, right? So by default, I'm going to jump to this, but let's say we have x is equal to 6, or let's just say x is equal to 12, and a is equal to 2, like we have here. Then how many numbers are strictly smaller than this one, right? Well, it's not 12 divided by 2, it's actually 11 divided by 2, the 4 of that. So that gives us, this. And then the other component is, obviously some symmetry. I don't have to prove it, or, you can prove it at a slower pace if you get. And then x. So you have these two things. Oops. Right? And of course, we should probably cache this so that we don't have to calculate it all the time. Right? Yeah, and I'm just double check. Yeah, okay. So I'm working in my head whether this is, how many duplicate numbers are there smaller than this one. So basically, this is the number of small numbers that's smaller than A, the number smaller than B, and how many dupes. So then you just have to, sum this up. Obviously, you sum these two components. I always put parens. I know the order of operations, but it also makes things readable, I believe. And then you subtract the duplicates, and this is. Yeah, this should be good, right? And like I said, for more than 2 numbers, you use something called the inclusion exclusion principle. But yeah, and then now we can do a binary search. So we can left and right is equal to. So this part may be a little bit tricky because now we're trying to figure out the bounds by which we set the right. And in this case, n is 10 to the 9, so, and b is 4 times 10 to the 4th, right? And that means that if we draw out the sequence where b is 4 times 10 to the 4th, and there's 10 to the 9 of them, then it's just these two numbers combined or multiplied by each other. So roughly speaking, it's like 4 times 10 to the 13 or something like that, maybe. But the beauty is that you can actually, as long as you're pessimistic in terms of, going further off, you always get a right answer. So I'm just going to opt for this. It's a little bit slower, but that's fine. Yeah, and then now we're going to do our binary search. And note that this fits in the long, so even though they want you to return it mod this number, and also actually before I forget, let's actually do the mod thing, because I forget a lot actually, and usually I do a little song, but today I did not. Okay, so yeah, so what was I saying? So this fits in the long, so you don't have to worry about big int or anything like that. So I would be confident in most languages. And you do this. This is regular binary search. And then the question is, okay, how many magical numbers are smaller than, in this case, x? And this may not be the question that I asked, to be honest. Let me think about this for a second. So let's say we want to try to figure out the magical number n, right? So then we ask ourselves, okay, given, not x, whoops, mid, how many, what do we want, right? If this is, so the nth magical number would have exactly n minus 1 magical number smaller than it. So if it's equal to or greater than this, then that means that, what does that mean? That means that this is now an upper bound, right? Because every number that's bigger than this will have more than n minus 1. So now we can move the upper bound down, and that means that n is inclusive because f of mid is f of mid equals n minus 1 is a possible answer. So that means that this is inclusive, so we do this. And then otherwise left mid is not a possible answer, and that's why we do mid plus 1 like this. And that's pretty much it. Yeah, And so the reason why I hesitate a little bit when I saw the mod is because if you needed to do big int or something like that, I mean, in Python actually it's okay. And I probably should have proved this back first, to be honest. I did this a little bit in a weird order for you all. But because you cannot do the modular before the binary search, right? So that's why it's a little bit awkward if you need to do it with big int. I mean, you have to do it with big int. You cannot do it with modular, right? So, but now with this, I am a little bit more confident. So let's give it a spin. And of course, we'll do a big case later. We just want to check at least these base cases. And I got the wrong answer, so I feel a little bit sad. Am I just, off by, Welp. That's a little bit sad. Oh, I was wrong on this one, I think. Yeah, so basically, yeah, I mean, I looked at two relatively prime numbers, and then I went, oh, okay, yeah, you just multiply them, duh. And that's why sometimes, you gotta validate things. And I went a little bit fast because I was, my excuse is that I'm shooting on video, I'm doing it live. But yeah, but now as soon as you see this, you know that you actually want the least common multiple, right? For example, and you can play around with examples here, but like for example, I didn't even see the examples, but that's what I imagined. But and I'm off by 1 to be honest. So I've double checked that. That is a little bit awkward actually. But anyway, we'll double check the off by 1 because usually that means that I'm asking the question wrong and then as a recording. But let's say, for example, this is, I don't know, something that's, let's say 6 and 8, right? I want something that's not a multiple of each other. So A times B is obviously 48, but LCM of AB is, what is this, right? Well, 24, right? So of course, we're going to undercount actually, because if you just, what is it, 6, 12, 18, 24, 8, 16, 24, Well, of course, this is a dupe, but we are now formula. We did not calculate the dupe. So we just have to do this by getting the, getting the least common multiple. And then this should be good other than the off by 1, which we'll look at in a second. But we can verify that at least it's consistently off by 1. So then my question is, did I ask the questions incorrectly? Right? Why is this off by 1? I mean, of course, I can just do a +1 or whatever, but I actually want. But usually that means that there's my understanding of the binary search is a little bit off, or just in general. I mean, it doesn't have to be a binary search problem for it to be off, but it is some, an indication that something's off. And for me, especially when I'm trying to teach or whatever, trying to understand why that is and stuff, just be like, oh yeah, just add 1 and then we're done, right? No, I mean, try to understand it a little bit. Because my understanding was that, okay, so that means that this part is probably a little bit off, because that's the only place that we really make a decision. Let me think about this. I mean, this is inclusive, so that means that mid is a possible answer. So why is it that, and if this is smaller than n, we need a bigger n-1. Did I mess up the n-1 part? Because we want the first number essentially, in which f of mid is greater than. Oh, okay, I see. I actually messed up on this one because I asked the wrong question. Okay. So actually, I don't know if at +1 works. Maybe at +1 works, but now my understanding is a little bit better, and I think I got it wrong, and I see why I'm wrong, and I'll explain why I'm wrong. And actually, I think this will be this is a good lesson to kind of figure out off by 1s, I think, maybe. But what happened here is that, for example, what I ask is so what I end up asking here is actually, what is the smallest number where there is n-1 magical numbers smaller than, right? So English is a little awkward, but hopefully that that gets my point across, where that actually isn't true. I think innately, because I was thinking about the first thing, but actually that's not true, right? Because, for example, let's say we go back to here. If we were here, let's just say we're looking for, I don't know, the 6th number or something, the 6th number, or even, doesn't matter, just the 5th or just the 2nd number. That means that we are asking for what is the smallest number in which there are one smaller magical number, right? And that means that if you put this in a list, a sorted list, then the number is actually 7, right? So this actually returns 7 instead of this actually returns 7 because 7 has one smaller magical number. So actually what we want is the largest number where this is the case. Of course, there are other ways to solve it. There, for example, you can actually make this like smaller than or equal to. Then you want the first number because then you get the first number, which is equal to n exactly n or because if you set this to smaller or equal to, then your question becomes, what is the smallest number in which this is equal to n? And that also solves the problem. But so there are multiple ways to kind of resolve it, and that's why I say it really matters how you ask the question and like state these questions out. And yeah, and now we now change the question to what is the largest number, right? And then what does that mean? That means that if this is equal, let me think about this for a second, right? If that means that if this is equal, then we actually, so now we fix this a little bit, because if this is equal, that means that if this is equal, that means that this can be bigger, right? So now our thing is a little bit awkward. I mean, you can split up into a ternary thing, and I'm going to do that just for illustration because I think the right way is to switch the signs, and it might not make sense. So I'm going to break it down a little bit more. So let's say we have this function from the previous one. We'll break it down a little bit. So let's say we have this, and then else if, because I want to demonstrate very clearly why. Right, so this is equivalent to this, and I think this part is not that much of a leap. Yeah, but then now this is for smallest number, right? Now we want the largest number, and then now we have to think about the cases, right? Well, if this is bigger than n minus 1, what happens? If this is bigger than n minus 1, then this is true. Is this true? So I'm confusing myself for a little second. At least in terms of explanation. So what is the largest number with this is the case? So if this is bigger than that, then actually this is not possible. So this is right minus 1, right? Because we want something that's exactly n minus. Yeah. We want a number that has exactly n minus 1 items, right? So we convert this to right equals mid minus 1. What happens if it's equal to? Well, if it's equal to, then actually in this case, we want left is equal to mid, right? Because now if this is equal to n minus 1, then our number, because we want the largest number, we want it to be possibly to go up, right? But mid is a possible answer, but it may not be the largest number answer. So that's why we're going to set it to this. Otherwise, if it is smaller, we set left is equal to mid plus 1. Yeah. And I think this will give us the answer. Though, of course, the reason why I wrote this a little bit awkward is that you can have also switched the signs if you're really observant. And actually, left is equal to mid minus 1 plus 1 is fine. But if you want to be pessimistic, you can also just remove the plus 1, and then as a result, this is you could roll this into that, and that means that you just end up being this thing, right? And that's the short way of doing it. and that's what I was thinking about writing. Actually, I was thinking about like switching the signs in a different way. But yeah, that should work in theory, unless my understanding is off again. So let's give it a spin. Yeah, so that looks good now that we really understand why we write these if statements, right? And I think that's one thing that comes from practice and me going over it. Hopefully will give you some insight as to how these things are. Because I think one thing that happens a lot is that you see these if statements and people just kind of give you like random things, and they just tell you why it is, and they just go whatever, right? And like I said, yeah, so these if statements have meaning, and I hope going through it in a more deliberate pace will help you out. And of course, these if statements also depend on this question, and this question also depends on this question, right? So they all follow through, and so if certain things are a little bit different, you may actually have slightly different answers, right? Because, for example, if you don't use n-1, you use x over a instead, then this is smaller than or equal to, and that makes the question different to get your answer. Yeah, so now let's actually try a number that requires modding. So yeah, let's just do 2, 3, and what's it, 10 to the 9? Wait, n is first, right? So, oops. Yeah. Okay, so that looks good. So I'm or happier. I don't know. Let's do one where they're not mutually they're not mutual. They're not relatively prime. That's what I was gonna say. So that still looks good. So let's give it a submit. Well, I haven't done this one before. I mean, I haven't done this one before on Leetcode. I have done similar prompts before. So yeah. Day 620 streak. Yay. Yeah. Of course, the complexity is straightforward for a binary search. We look at the search space, and this is constant in the size of the search space, I guess, or log of the u, where u is the size of the universe, which is the range, which is 10 to the 14. So let me write it down. Log u time, where u is the size of the universe, which is the range of 10 to the 14, say, right? And of course, space, this is just O of 1 because we have a couple variables and that's it. You can also analyze it in terms of the number of digits. I'll leave it up to you at home, but it's gonna be linear. Is the short story. If you want to analyze it in terms of number of digits, so yeah. Anyway, I think that's all I have for this Friday or maybe Saturday to y'all. Hope y'all are doing well. Stay good, stay healthy, to good mental health. Hit the like button, hit the subscribe button, and join me on Discord. Take care of yourself. I'll see you later. Bye-bye.